Welcome to our masterclass. My name is Robin Young. I'm the publisher of Orthopedics This Week, and I will be your moderator for today's masterclass. We have an excellent master faculty with us to discuss the future of peak additive manufacturing with Invibio Biomaterials Solutions. And this masterclass will be exploring the clinical possibilities that peak additive manufacturing is already opening up for spine and orthopedic applications. This is a particularly timely subject as we've seen a number of innovative porous and additive manufactured PEEK implants for spine fusion, which have recently begun commercialization and have been met with strong surgeon acceptance because these novel implants maximize the clinical benefits that are achievable with PEEK implants. Secondly, the partnership of Invibio with Bond 3D, who developed a unique and differentiated 3D printing process with Peak, has recently helped their first customer file a 510(k) for a cervical and lumbar interbody system, the first utilizing the Bond 3D technology. So I'm really pleased to introduce our master faculty today, starting with Professor Bill Walsh, who is the professor at the Surgical and Orthopedic Research Laboratories at the University of New South Wales in Sydney, Australia. And I would add, parenthetically, everybody's favorite researcher for what he does, widely recognized, and that's an understatement, widely recognized expert in biomechanics and biomaterials research, focusing on the interface between implanted materials and connective tissues of the body. Also joining us is Dr. Mark Brady, the additive manufacturing program leader for Invibio Biomaterial Solutions. Mark has been with Invibio since 2010, where he held a number of product development and strategic technology roles. He received his undergraduate degree in biochemistry and a PhD from the University of Liverpool in the United Kingdom. So this is going to be a particularly interesting masterclass, I think. So to our audience, as you listen, I know you're going to have questions. Please make frequent use of that Q&A button right at the bottom of your screen. So starting us off will be Dr. Mark Brady and his talk, Peak for Additive Manufacturing, a Peak into the Future. So it's my great pleasure to introduce to everybody Dr. Mark Brady. Mark, the podium is yours.
Thanks very much for the introduction, Robin. I'm really pleased and honored to have the opportunity to give you an overview of Invibio's activities in the additive manufacturing space for PEEK and how we're working together with our key partners to bring our customers' innovations to market and address some of the unmet clinical needs that we see or deliver health economic benefits. What we hope to leave you here today with is a sense that Invibio is a trusted partner in that journey towards realizing the potential of peak additive manufacturing in delivering improved clinical outcomes for patients. We truly believe that only through bringing together all the right elements and expertise from material science through to manufacturing and validation capability within an ecosystem to deliver finished, safe, and effective parts can those goals truly be achieved. Central to that ecosystem is the investment by our parent company, Victrex, who first commercialized PEEK over 40 years ago now in Bond 3D. And Bond 3D are a company based in Enschede in the Netherlands who've developed a differentiated extrusion-based 3D printing technology. The combination of the in-house developed hardware and software from Bond 3D enables printing of virtually void-free PEEK parts. What also comes with that is high isotropic strength. And finally, the proprietary software provides design freedom and placement of porous structures and infills in ways that are not currently achievable with some of the commercial slicer software packages out there today. One of the areas where we're seeing the Bond 3D technology differentiating from other PKM technologies to deliver value is in the interbody fusion space. The Bond 3D process may be able to address that clinical need for bone ingrowth via porous structures to establish earlier integration and stability, so participating more in the fusion process, but without compromising on some of the inherent mechanical properties of PEEK. At the same time, surgeons can continue to evaluate post-operative fusion progression with greater confidence on plain radiography or without artifacts that are often encountered on CT or MRI with metal implants. So over the next few minutes, I'm going to give you a brief introduction to Invibio and our mission. I'll then go on to briefly introduce the two main additive manufacturing routes available today with Peak, as well as some of the challenges there, before moving on to highlighting Invibio's activities in the additive manufacturing space. And I'll be focusing predominantly on the Bond 3D technology today. After that, I'll cover a key application focus for us at the moment in interbody fusion, and then I'll bring you right up to date with our current status. So for those of you not already incredibly familiar with Peak, Invibio's Peak Optima is now being used in approximately 15 million devices worldwide from head to toe. So from craniomaxillofacial and dental applications down to foot and ankle wedges. It's got some key inherent properties that make it eminently suitable for these applications. And it can be tailored to improve various aspects, whether that be improving bone on growth or fatigue strength, for example, in some of our trauma applications. It can also be processed into a range of forms for different manufacturing processes, including additive manufacturing. So why Peak Optima? Well, it sits at the very top of the pyramid of high performance polymers. It's got some unique combinations of properties which make it suitable for a whole host of permanent implant applications. Some of the key ones being biocompatibility, a modulus close to bone, thereby reducing stress shielding, and artifact-free imaging. That's allowing surgeons to monitor the healing process unimpeded. With over 20 years of proven clinical history with Peak implants, we're starting to transition from being a biomaterial supplier to a partner for innovation in all stages of the product lifecycle. So you might be aware, for example, that Invibio has partnered with Max Orthopedics to develop a Peak Optima femoral knee component, and also with Interbones to develop extremity implants using our composite technologies. Additive manufacturing Peak expertise is the next step in enabling our customers' development goals. So when we look at the main additive manufacturing routes that are applicable to polyaryl ether ketones or PAKEs, there are two. The first is an extrusion-based one, the most common being fused filament fabrication, or FDM, and the other is powder bed fusion, or selective laser sintering. Both of these build parts layer by layer. In filament fusion, that's through feeding filament through a heated nozzle to melt the material and deposit onto the surface, either onto the print bed or onto a previous layer. In selective laser sintering, that's by heating a fine powder by a laser to pass the melt temperature and fuse the powder into a part. They both have their advantages and disadvantages, but it's perhaps because of the lower machine costs and the easier feedstock handling that it's made that investment in fused filament fabrication has been more common. So not every part is necessarily suitable for additive manufacturing, and part selection is key to a successful outcome, both in the end product performance and also in the economic value that it brings. Those parts that need to meet certain functional performance criteria, for example, load bearing, or where the value of the part offsets the initial investment, or the parts are relatively small and complex. For example, they include, complicated features or porosity, and where it intersects with Peak being specified based upon one or more of its characteristics. These are the perfect candidates for Peak additive manufacturing. But printing with Peak isn't a slam dunk. It was originally designed, Peak, for traditional manufacturing routes. Its high melt temperature of around 340 degrees, fast crystallization speed, and relatively high viscosity at the low shear rates observed in fused filament fabrication make it a very challenging aspect to retain the benefits of the native Peak. And you need heavily engineered machines which are capable of nozzle temperatures of 350 to 450 degrees C plus. And they're needed together with build room temperatures of up to 250 degrees centigrade to be able to control that recrystallization speed and achieve the semi-crystalline parts with native peak properties. You also have to design differently to a subtractive manufacturing approach or even powder bed fusion, so that processing knowledge needs to be developed and it's not a plug and play solution. At Invibio, we believe investment in research, collaboration, and partnerships are all key to a successful outcome in peak additive manufacturing. Part of that is in fundamental research and strengthening our own materials knowledge. Our parent company, Victrex, has partnered with Exeter Technologies Group at the University of Exeter in the UK. And this includes the Centre for Additive Layer Manufacturing, or CALM, which is the UK Centre of Excellence in High Temperature Polymer Additive Manufacturing. We're also introducing new forms for additive manufacturing, including a medical grade peak optima filament, as well as feedstock for the Bond 3D technology that we've invested in. Bond bring with them a wealth of experience on their platform to enable design for manufacture, and Invibio have internal testing capabilities for applications in spine and beyond. Elsewhere, we're partnering with other contract manufacturers for volume printing and part finishing. And finally, we can provide the regulatory support, and have just strengthened our offering here by filing a new master file with the FDA, which covers the Bond 3D printing feedstock and also the Bond 3D process. So I've talked about some of the challenges printing with Peak, but for those who already have a Peak capable machine, or they're willing to go on that journey to invest on establishing technology in-house, Invibio does offer a Peak Optima filament. And this enables our customers to take advantage of a 1.75 millimeter filament offering, which meets the needs of fused filament fabrication. And it allows them to design complex devices for point of care, patient match devices, or serial production. All of that leveraging the benefits of trusted Peak Optima polymers. Now, if we turn our attention to Bond 3D and their technology, this is the Bond differentiated technology. This is the Bond machine, which is built in a rather modular fashion that allows easy upgrades, maintenance, and repairs. In the center of the picture there, you can see the build room, and that's capable of reaching up to 250 degrees C. And it's got a build space of up to 400 by 400 by 400 millimeters. In the top module are the print heads and the cartridges that hold the Peak Optima feedstock. And over on the right-hand side is the process monitoring panel. Here, every sensor in the printer is continuously logged and can be retrieved for quality purposes. There's also the ability to visualize the build through the camera link on the panel. So what differentiates Bond 3D? Well, for some high-end printers, they've still struggled to print with Peak, and sometimes the materials had to be modified to meet the machine capabilities. And so, for example, Victrex have introduced a low melt PAEK, which is very similar to Peak, but it has some of the building blocks in the polymer backbone rearranged. And that allows you to open up the processing window a little bit. Bond, however, from the get-go, have focused on developing their machine and process to meet the existing materials, including Peak Optima Natural. One of the things seen in conventional fused filament fabrication is that in an effort to hit perfect extrusion without voids, there's always some fluctuation towards under or over extrusion. Over extrusion can be disastrous. It results in a bow wave of material in front of the print nozzle, and that can eventually drag the whole build off the print bed. And so many printers are calibrated towards a very slight under extrusion. So let's take a look at the impact of that under extrusion on the critical part strength in the Z direction. If you take a first layer, for example, you can see the slightly elliptical shape of the deposited filament when you look end on. And then the second layer is often laid down at 90 degrees to the first layer. And with traditional flow control printing, where the materials meted out consistently and calibrated towards slight under extrusion, you can get these areas of limited contact between the layers. And that can leave voids and can have an impact on the subsequent Z strength, the most challenging area where you need to achieve high strength, and that can result in delamination. The bond technology uses alternating traditional flow control printing with pressure control printing to achieve virtually voidless parts. Flow control is used to deposit tracks either side, and then a pressure control printing track is deposited between to achieve perfect fill. And this is all controlled via a feedback loop between the force applied to the feedstock in the feeder and a preset pressure value that's experienced in the melt pool between the nozzle and the substrate. What that means is that via the pressure control printing process, you can achieve perfect fill of small, medium, or large gaps between the flow control lines. Under microscopy, you can really start to see the effect that has on the presence of voids that can be encountered. On the left-hand side, you've got the conventional fused filament fabrication, and on the right-hand side, the consolidated parts that are achievable with the Bond 3D technology when the pressure control printing is deployed. And here on the right-hand side, you're meeting void levels which are comparable with injection molded parts. And so when we look at how that then translates, all of this goes across to excellent mechanical properties, isotropic strength in tensile, including in the Z direction, which is really the Achilles heel when it comes to fused filament fabrication. And it's the most challenging direction to get high strength with PEEK. The other element that Bond have developed in-house is their slicer software. So the slicer is what takes the CAD model and the print parameters. So for example, the layer height, the speed, the infill structures, and it translates those into the G code for printing. And they've needed to do this since the commercial slicers don't allow them to lay down these alternating flow and pressure control lines within a single layer. The process allows them to optimize that printing for virtually voidless and strong parts. As I mentioned before, to get the most out of 3D printing PEEK, you need to have the knowledge and the experience in designing here. And Bond have in-house experienced application engineers that can help translate from an initial concept to functional parts. And there are, of course, some generic principles that apply with any fused filament fabrication approach, as well as some specific ones that are specific to the Bond technology that also need to be taken into account when designing. Turning our attention now to one of the key application areas where we see the differentiated Bond 3D technology adding value, and that's in interbody fusion. If we look at the history in the trends in interbody fusion when it comes to materials, from the early 2000s when PEEK Optima was first introduced, there was a steady growth in its uptake in interbody fusion devices. And that's largely owing to the imaging properties and the stiffness advantages over solid titanium cages. By the middle of the 2010s, however, we saw titanium use increase. And that was partly due to a trend towards expandable devices, but also accessibility of titanium 3D printing that enabled the ability to create new features, porous structures, and the ability to be able to modulate some of the device stiffness. We saw the first attempts to create PEEK-based devices, but they were very much still in their infancy, and the non-additive manufacturing approaches to porous PEEK still had some design limitations to them. Today, we're seeing PEEK additive manufacturing capabilities starting to mature, with Bond out near the front. Together with Bond and other partners, we've been co-developing an interbody fusion range aimed at market entry in 2024. We filed a master file with the FDA, which extensively covers the feedstock materials and the Bond 3D process. And we've completed a preclinical lumbar fusion study using the Bond 3D technology, which Bill is going to present on next. When we first started working with Bond, we wanted to understand their capabilities in an application. So we started with a non-optimized PLIF cage design. And I need to be really clear here that this is a design that we have no intent to and had no intent to develop for clinical use. It's just used as a tool for evaluation of the Bond technology. And you can see how Bond took the design, broke it down into different bodies and applied their pressure controlled printing in the solid sections, and then deployed their porous structures elsewhere, not just on the end plates, but on the vertical planes within that graph space as well. And we looked at mechanical properties as well, and we played around with different print strategies and post-processing, for example, annealing processes or machining some of the detailed features to look at what the impact was on mechanical strength. And then we really started to challenge the parts in axial compression and shear compression. And what we found was that these could hold up to some of the challenging shear compression tests, where the interlayer adhesion strength was really being challenged, both in static and also in dynamic testing. And the parts managed to meet the published anonymized data from the FDA that came in the PEC paper from 2018. Again, we used the generic PLIF device to understand bond reproducibility and printed features, and found that pore size and track width were really well and tightly controlled. So the freedom to design there is achievable because of the unique capabilities of the Bond 3D printer and the versatility of the slicer software that enables some features that we couldn't otherwise be possible to replicate in commercial slicers. So the freedom to design is really there, and it's achievable because of the unique capabilities of the Bond 3D printer and the versatility of their slicer software that enables them to achieve some features that would otherwise not be possible with existing slicer software. So you can achieve simple lattices like you see here on some of these demonstrator parts. Taking a closer look at some of those lattices, just alternating and changing up the spacing and the sizing of those pores, changing towards curved tracks, which allow a more organic look to our parts, and just looking at a little bit more detail here, just really how controllable and consistent the features are that can be achieved as we move into porous structures, all the way to even more organic forms and gyroids that really start to take on the appearance of more trabecular looking features. And when we start to look at the printed surface under scanning electron microscopy, we could also start to see some of the macro and then some of the micro topography. So offering a different surface to machined or injection molded PEEK that might conceivably play a role in osteoblast adhesion and bony integration. So what could an additive manufactured porous PEEK deliver? Well, we'd certainly retain some of the inherent benefits of PEEK Optima today in stiffness and in imaging capability, though we might now be able to further modulate that stiffness to get a closer match to the host bone where it's needed. Design freedom would also allow us to introduce porosity that may allow us to achieve bony ingrowth to achieve earlier fixation or stabilization. We know from some previous studies that bone will grow into porous PEEK structures, both from our own studies here at Invibio and from some of those technologies that have now gone on to be commercialized. In some of those studies, it was shown that the addition of a thin titanium coating resulted in similar degrees of bone ingrowth, but no increase in implant fixation, suggesting that it's really the structure rather than the chemistry that's the driving force. And we can see in some of the non-additive manufactured porous studies that we've done in the past, with bone growing right into the porous features in this long bone study that we performed with Bill Walsh some number of years ago now. And this is as early as 4 weeks after implantation. And whilst we haven't got 100% continuous contact between the PEEK and the bone, there are areas of intimate contact between the bone and the PEEK with no intervening fibrous tissues. So bringing us now right back up to date, we've concluded a new large animal study, which Bill's about to present on next. Invibio's also filed a master file with the FDA, extensively covering the PEEK Optima feedstock and the Bond 3D additive manufacturing process. And that's there to be able to support any future 510K submissions. And then finally, I'm really pleased to say that our first customer, Envision Biomedical Technologies, has recently submitted a 510K for the first Invibio Bond 3D additively manufactured interbody device following a co-development. And then I'll bring us back to this idea of partnerships, going full loop now. We want to be able to re-emphasize the importance of these collaborations and partnerships to speed the development of safe and effective devices, to bring them to market, to address unmet clinical needs, and to deliver some health economic benefits. And finally, I'll just leave you with the key takeaways that I started this presentation with. Thank you for your time.
Thank you, Dr. Brady. That was really excellent. I learned a lot. Not only the way that the new additive manufacturing approach expands the design capabilities, but this proprietary technology from Bond 3D, which provides, as you pointed out, the voidless printing of Peak, just outstanding. And I think the way that you presented the issues and sort of walked us through how the issues develop and how the Bond 3D approach really delivers the strengths that's required, but still keeps the miracle of additive manufacturing, namely allowing for porous features and giving design engineers a lot of space to be creative and come up with something that is more clinically relevant. Really, thank you. I really enjoyed your presentation very much. Okay,
Thank you.
our next speaker is Professor Bill Walsh, and his talk, 3D printed porous peak in the ovine lumbar fusion model, is up next. Bill, it is just terrific to have you part of this of our masterclass today, and the podium is now yours.
Good evening or good afternoon, everyone. And thanks, Robin, for that nice introduction. And I'd like to congratulate Mark on an excellent presentation. And it will allow me not to discuss all the nuances of additive manufacturing that he did cover. I'd like to welcome everyone to my presentation. Just putting it into context where my lab in Sydney, Australia fits into the ecosystem is we love evaluating the technology to participate in not only the design, but the evaluation of it so that we can ultimately provide the healthcare system with the best type of products to improve patient outcome. And I'd like to acknowledge my my colleagues and collaborators within my laboratory here, and also Mark and Mike Veldman from Invibio and Nick Cordaro from Spitrex. So where do we begin? Well, I think Mark gave us a great overview on 3D printing, so we can kind of skip that. But we do have to consider porous materials. We do have to consider the type of material, PEEK or titanium. And we also have to consider the type of model that we're going to put it into. And we also have to consider, obviously, lumbar fusion, which is the application that I participated with in Invibio to evaluate a 3D tie versus a 3D PEEK printed implant. I always like to begin with some questions for everyone is what you see, what you get. All right. So when you look at an X-ray or a CT scan, is what you actually see on the X-ray or the CT what you get? And I put it to you that it is important to know what you see so that you can monitor the progression and make decisions from a clinical perspective and or a design point of view to either move your technology closer to the market or to move it to be more efficacious for patients. So keep that in the back of your mind. And I also like to think about evolution and biology because being a professor type person, in biology, there's lots of evolutionary pressures to change shapes and structures. Species become extinct all the time. And I'm a big fan of fossils and bones. I have bones all over my office. And extinction from a biological point of view is complete disappearance of a species from Earth. But if we correlate that with medical devices can become extinct, but they often adapt to either the better understanding from the clinical world or the improvements in technology, as Mark very elegantly alluded to, how the improvements in additive manufacturing of polymers has come a long way. And when medical devices evolve, they evolve through all the different evolutionary pressures or the market pressures that are there. But we also can have implants that become end of life and they become obsolescent. But the evolutionary pressures to design and clinical use implants is not just related to the material or the structure. It's related to how it can be monitored clinically, what the costs are, how the technology is adopted, what are the regulatory concerns to do it, and ultimately, what are the costs? So when we look at, well, how did I get here, or how did we get here? We got here in my lab in Australia by doing bone integration, osseointegration for the past 20 odd years, close to 30 years. And we have been doing the same model since 1997. And we have been looking at different materials, be it cobalt chromes or porous titanium, porous tantalum, PEEK, modified PEEK, PEEK coated, and all the different ways that companies and scientists around the world could potentially improve integration or fixation at the bone implant interface. And we still do this model to today. We have a number of studies currently running with this. And my lab does a lot of other bits and pieces, but we'll just stick to the script. When we think of a material, be it a hip replacement, a knee replacement, or an interbody cage, or even a screw, we have solid materials, porous materials, coatings, and now we have with additive manufacture the opportunity of new and complex structures. But if we think at traditional manufacturing really can satisfy almost all of them except complex geometries, just due to the nature of the technology. And additive manufacturing can basically cover all of them as well, but you can't directly coat something in additive manufacturing yet. I'm sure that there'll be a paper in the next couple of years where people are doing a 3D print and then doing a coating. I'm sure that that kind of technology could be developed. But I want to just kind of go a brief overview. We've been using this model for countless times, and this is 3D porous titanium beads with hydroxyapatite, the original DePuy Porocoat. And we looked at the mechanical properties and the benefit of adding hydroxyapatite, or the potential no statistical difference, but a benefit on a grit blasted structure. This is a smooth structure. And we've looked at different coating thicknesses with the exact same model, changing the plasma sprayed coating of hydroxyapatite from 50 to 150. Again, classic hip replacement stuff that's all been out in the literature for years based on these type of tests. But we've also used additive manufacturing with this model. I jumped, 10 years, and we've worked with different groups. This was a three-dimensional titanium implant that was done with traditional manufacturing. From what I understand, very expensive, but you can make a 3D porous titanium implant with traditional manufacturing. And what you see with these implants, that in a cortical site on the top here, bone grows right through the cortical site. But on a cancellous site, the bone really doesn't want to grow through even a porous material. And we jump to another paper. This is another electron beam melted implant that has a three-dimensional surface on the outer core of a solid titanium implant versus a plasma sprayed. And again, additive manufacture, traditional manufacture, again for arthroplasty. And we can look at all the different components of that. And it really, now I jump to 2012. This is some early work that we did with Invibio on porous PEEK, made with, I'll call it, traditional manufacturing techniques. Some issues with respect to connectivity and tortuosity and mechanical properties. But, additive or 3D metals and 3D plastics have been around for quite a while. And we put that in to the exact same model that I've shared with you previously. And again, looked at osseointegration and mechanical properties in cortical and cancellous sites. And we showed osseointegration is possible with porous PEEK. And Mark shared some of these slides with you. This is bone integrating in a cortical site. And you can see that the bone grows through. And this starts to make me think of macro topography being an important component. The space between the material is probably just as important as the material itself, because then the bone can interdigitate into that and grab a foothold to achieve fixation. Here's another 3D PEEK study we did, just an excerpt of a histological slide. This one was porous, but it wasn't connected, right? So bone did not osseointegrate into this. So the manufacturing method does make a difference. So again, we do have some fibrous tissue in there and a little bit of bone, but the connectivity of this was in a different direction relative to where the bone wanted to grow through. Now we jump to this paper we did with our friends Greg Causey from Applied Medical. This was an interesting study where in this, using the exact same model that we had for now for 2 decades, we changed the geometry of titanium material with an electrochemical grinding process and made macro topography implants, and we put it into the same model. And we look at the mechanical properties, and you can see that the geometry dictates or drives the biomechanics. And then again, in the cancellous bone really only grows a little bit in cancellous sites. And a follow-on paper that we did with Greg, where in this study, we actually have PEEK with 2 different geometries. PEEK that had hydroxyapatite on it, titanium-coated PEEK, solid titanium machined, electrochemically grinded, and polyethylene. And when we look at that, all the materials supported osseointegration, even the polyethylene. The polyethylene, when we pushed it out, deformed, but it supported osseointegration. And we even see that in our micro CTs, because there's no metal artifact either with the polyethylene or the PEEK, but we can see osseointegration or bone growing into the available geometry that the implant provides. A recent paper we did with Cambry Kelly and Ken Gall, now moving to metal additive manufacturing with gyroids and segmental defects, and another paper with Cambry and Ken and my team, where we varied the porosity of a gyroid that was titanium 3D printed, and we looked at the effect of the porosity of the gyroid on fixation, both in cortical and cancellous, and there is an optimal porosity for a TPMS type of structure, again with the exact same model, so it's nice to compare them. You can probably even overlay all the graphs that we've ever published with it to make it easy for you. So we can see a lot. Now, this is an interesting paper where we started thinking about, does it matter? We know from our previous work that cortical bone and cancellous bone does not respond the same. So when you get to someone like me, when you're evaluating technology, you want to understand the models that you're looking at and how you use them. So our cortical and cancellous integration reflecting of the spine. So we did this experiment where we had an additive manufactured dowel and then an additive manufactured inner body cage with the same exact pores and structure and surface. You can see the SEMs there. And we put it into cortical bone. We put it into cancellous bone. Then we did an end plate sparing inner body fusion model, which is what I did for the current study that you'll see in a few minutes. And we filled it with either autograft or allograft, and we backed it up with posterior pedicle screw fixation. Just showing you the results of this quickly. And this will be interesting for you to remember, is that when you have metal and you try to do micro CT imaging, it's often difficult to tell what's actually happening in the walls of the device, but also in the aperture. We're not really 100% sure if that's all bone because it's metal. It's just hard to tell. And I can tell you it's hard to tell because I've looked at thousands of these and compared them to the histology, which we will go a little bit further. So it's very difficult. And when you look at the in vivo reaction in a cortical site at 4 weeks and a cortical site at 12 weeks, we get osseointegration. Cortical bone wants to be bone. But when you go in cancellous bone at 4 weeks and cancellous bone at 12 weeks, there's really no driving motivation for the bone to integrate through that cancellous or that architecture of the 3D printed substrate, even though the bone does love titanium. It loves the titanium at the interface. And if we look at the inner body fusion histology, again, this will be reflective in what you see in our current study. There's really not a lot of bone in the walls. And when there is bone in the walls, it's very difficult to differentiate it based on CT scan or micro CT scans. And then a final quick study. Again, this is a study that Matt and I did with our team and Frank Vizeschi and Schaefer from C-Spine. This is a macro topography implant where fixation is dictated by the geometry and macro structure. This is PEEK coated with nanometalline, which is a thin titanium coating. And again, end plate sparing model backed up with pedicle screws. And just to illustrate that the geometry drives the fixation and then ultimately facilitates the inner body fusion in the aperture. So the little interstices or the macro topography features can get captured. But we can see everything here because the nanometalline is not visible even on micro CT because it's such a thin coating on PEEK Optima. And so what do inner body cages do? I think everyone knows that they hold the bone apart and they contain the graft, but originally they were not designed to participate in the fusion. But, in 2015, there was some literature out there that says maybe they could actually participate in the fusion. And that's really where we're at in today's world. So where are we now in 2024 with 3D printing? and how far has it come? I think Mark's talk really laid the foundation. 3D printing with polymer, with PEEK, has come a long way, a lot further than I think many people realize. But what about other techniques? What about other technologies? All of these potentially influence the clinical outcome. So you can't have a silver bullet in any of this stuff. So we get down to the evolution of interbody devices. Everyone has probably seen these classic images of the original cylindrical cages, and then titanium-coated PEEK and waveform, and another newly released 3D printed PEEK device that's out on the market now, titanium-coated PEEKs. Metal that's porous, that's not 3D printed, 3D printed metal. So there's all different implants out there, and there is a wide range of opportunities out there for surgeons to choose from. But understanding what the positives and the negatives of the technology are is important. And this is a classic comparison of PEEK versus titanium. PEEK is similar to bone. You can't see, it doesn't muck up your x-rays or your CT scans. But a lot of people think bone doesn't like PEEK. Well, that may not really be true. Bone likes PEEK, depending on the geometry. Ironically, bone does not really like super smooth titanium or super smooth cobalt chrome. We published that 25 years ago. But when it's a little bit rough, when it's a little bit porous, bone can grow into it. We're finding the same thing with PEEK. Bone will grow into PEEK and grab that bone and achieve fixation. Titanium stiff, it's difficult to assess radiographically. That holds true in hip replacements, knee replacements, trauma. So it's metal and bone, you can't see through the metal. It's very difficult. And again, bone and titanium, they have a great relationship, but it does depend on the design, the surface coating, the roughness. All of these can support integration. But now when we think about, can we additively manufacture both of these? And the short answer to that is yes. And that could be the end of my talk, that you can do it with both. Mark covered this. Additive manufacturing is a completely separate topic. I don't get into the weeds of all the different ways to additive manufacture. I get to the point where people provide us with the final finished product that they want to know, does it work and how does it work? So a little bit of 3D printing and implants. Cortical bone, a cranial defect is easy to do. It's easy to model. You can go with programs like Mimics or Simpleware. You can threshold the bone and easily print it in titanium as well as PEEK, and that has been done for many, many years. But when we start talking about cancellous bone, the cancellous bone architecture, as most of you probably will understand, it varies on what bone you look at, what orientation you want to take the slice in, what's the disease status, what's the age of the patient, because cancellous bone is porous, tortuous, varying in density, and even this is a T-Rex vertebral body. It even has cancellous bone in it, so cancellous bone architecture is conserved. I don't know if you can see me on the screen, but I was just holding up a T-Rex vertebral body. So all of these scaffolds that we have potentially out there are designed to mimic cancellous architecture, trabecular bone. But if you read the literature on titanium or even PEEK lattices, which one do you choose? What structure? Do you choose these triple periodic minimalization surfaces? They come in all different varieties. So it's actually quite complex, quite confusing on which one do you pick. What is the best lattice for osseointegration? What is the best lattice for mechanical properties? Is there a compromise? There's which one should you use? And that's where models that labs like mine can provide insight to the clinical world on what will be the potential clinical outcome successfully. There are tons of papers out there on additive manufacturing of PEEK. If you would have looked 10 years ago, you wouldn't have seen the 3D printed papers on PEEK. But if you look in today's literature, there's tons. And all you have to do is type in 3D printing and PEEK, and you'll get lots of literature, lots of references. But don't forget, some of them are going to be in other industries where additive manufacturing and PEEK is used in aerospace or other applications. So the information is out there. And what I like to think of how technology evolves, adapts, but how does it align? I showed you this from the work that Mark and Marcus and Steve Kurtz and Nick Cordaro and I did, nearly 13, 14 years ago, probably 15 years ago. If you think of, say, the blue line being additive manufactured titanium or a PEEK, and the orange line being PEEK, PEEK is lagging a little behind in its ability to 3D print. But if we look at in today's world, they're starting to align. Here's a recent paper from Steve Kurtz's team on fused filament fiber fabrication of PEEK, where they actually made, you know, the super complex tripper periodic minimal surfaces using a very, very inexpensive technology to print. And again, what Mark showed us today from Bond 3D, the elegance and architecture of what you can achieve with additive manufactured PEEK, completely different than what we were looking at, 15 years ago. So what did we do in this little study, and what can I share with you about the interbody fusion model we did? What we did was a standard model that we've been using in my lab for a number of years. It's a 4 to 5 year old female sheep. We do a 2-level non-consecutive interbody fusion with an end plate sparing technique that my friend Hyun Bae originally published, and then I followed on to him doing it the way he would say, "Do it right, Billy." And we harvested Allia crest graft. We had 2 groups, porous PEEK Optima, porous titanium alloy, and those are the images of the implants. We did 2 time points, 8 and 16 weeks, and we did endpoints of blood work, radiographs, micro CT to look at imaging and the positives and negatives, manual palpation, range of motion testing, and importantly, histology. But it's when you compare these endpoints and you compare against groups where you can see some interesting things happen. So this is just a micro CT of the 3D printed PEEK implant. You can see that we've got, porosity and availability at the interface. We've got our aperture, and we can look at it in different planes depending on where we slice it. This is sliced right at the side. This is sliced right in the middle, and you can see the porosity and the available areas for integration. And if we look at our animal model, it's a lateral approach, expose the disc, this is harvesting the autograft off the iliac wing, and then expose the disc, do an annulotomy, nucleotomy, prepare the end plates, crack the spine open with cast bar pins, put the graft in your cage, put it in and insert it so that the graft does not fall out, and then insert it, flip it over, put pedicle screws in. If we look at the results, we did manual palpation after we euthanized the animals. We removed the rods, and we did manual palpation. There was no statistical difference between PEEK, 3D PREEK, or 3D titanium. They both supported the fusion of the spine at 16 weeks, and they both were progressing at 8 weeks. And if we look at the radiographs and the faxotrons and all of our different bits and pieces, we had 1 titanium sample that had end plate resorption on X-ray radiographic analysis that turned out to be infected. We could not see the aperture in the titanium group, but we could see the aperture in the PEEK group. And micro CT obviously provided us more detail on 3D PEEK cages, but it was difficult to call it on titanium. So I will share that some with you with this. This was the case that had a titanium cage that was unfortunately infected, and we'll revisit that later. And there's the corresponding PEEK cage at 8 weeks where we can actually see the graft in the aperture, and we can even see a hint of osseointegration there. So if we look at this as a case that we did, this is the post-op fluoro. So we always do a fluoro to check the level. This is looking at the titanium in the 2 views, and then here's the PEEK. All we really can see with the PEEK is the graft in the middle of the cage. We can't see anything. And if we look at it when we euthanize the animal, these are the post-op radiographs and the cull radiographs. They're really almost of no value. All we can really see is that we have a block of metal there. We can't see the PEEK, and we can tell that the screws are relatively stable, no loose screws in the study. Then we look at faxotron radiographs where we harvest the spine and we have a slower exposure, longer X-ray detail. We really don't know what's happening in the PEEK, in the titanium, but we can see a bridge of bone in the PEEK. And I'll just cut to 16 weeks, same type of an analysis where we look at our post-op fluoros for the positioning, make sure there's no problems. And again, with the titanium, we really can't see what's happening inside. The interface looks like it doesn't have a fibrous tissue interface. The PEEK, we can see that there's actually an aperture, and we can see bone going from one vertebral body to the next. And then we look at micro CT. So again, titanium on the top, you can see the titanium, and PEEK on the bottom. You can't see the PEEK. All you can see with the PEEK is the bone going through the aperture, some areas of integration, bone growing through the aperture. With the titanium, what at least we notice on micro CT is that it looks a little fuzzy in the middle, and I'm not really sure what's inside the porous domains. There might be bone, but I'm not 100% sure. And we go on to 16 weeks. and we get the same story. Again, the fusions have progressed, but again, what's happening inside, it's easy to tell with the peak. It's more difficult to assess the aperture as well, but it's really hard to tell what's happening inside the porous domains. So we go micro CTs, we can have the opportunity to cut them in different orientations. What we did in this slice was cut the peak right at the top. And so this is looking at an axial view right at the top. And you can see just in the top of the cage, there's bone integrating into the porous domains of the cage. So we've got kind of spot welding happening, which is a nice sign of integration and stability. And if we cut this now just a little bit deeper into it, we can actually see the bone integrating into the porous domains of the device over here. And you can see more deeper spot welding, and it's actually going through. So it's actually grabbing, the implant and the bone are grabbing each other at multiple spots. And the final slice here is where we're cutting it in the coronal plane. And we actually, you can see bones streaming right on the outside of the porous bits of the implant right through here, connecting one vertebral body to the next. And you can actually, you can see the outline or the silhouette of the cage, but you can see right through it. So you can actually see the bone. And then this is corresponding histology at 8 weeks of osseointegration of the macro topography that the Peak 3D provided us. And again, now we move on to range of motion testing. This is where we use a robot and we just do range of motion testing. This is kind of classic, where we do flexion, extension, lateral bending, and axial rotation. And this is the raw data. And now this is the actual lateral bending, 3 cycles. We analyzed the range of motion going to the left and going to the right. Same thing with axial rotation. So don't forget, these are very small in axial rotation, and flexion extension. So this is an example of a 3D tie at 8 weeks, nice and fused. So when we summarize that data and we do lateral bending, again, 8 and 16 weeks, they're both a progression for both implants to progress to fusion, getting more stable. And there are no statistical differences either in lateral bending, flexion extension, or axial rotation. They both progress with time, and there are no differences within the groups, but time was a significant factor. And then we go on to histology. So this is serial sectioning of histology in the sagittal plane, Peak at 8 weeks, titanium at 8 weeks. We can see some integration, a little bit in the end plate there, disappointing, but that's only like a millimeter. But that's what we ended up getting on that case, again, on the end plate. And these are the corresponding SEMs. So we took the slice in between the histo and put it under the electron microscope. We can see osseointegration, nice osseointegration, a little bit of titanium caviar, but a nice fusion. And if we go on to 16 weeks, this is that case that was infected. That was the histology. But the CT scan looked like there was something there. But again, we'll revisit that. And again, 8 weeks, this is the corresponding site of that animal. If we go to 16, this is the SEM. And again, that's the case that was infected, and there's the Peak case that looks nice and fused in the aperture. We go on to 16 weeks, titanium on the left, Peak on the right, and you can see a nice bridge of bone in both cases, some areas of integration, and our corresponding SEMs. I like to do the nice kind of one-to-one comparison. What we see in the SEMs is we see a little bit of, I'll call it titanium caviar, that's on the surface of the implant that just kind of migrated out into the fusion space. With the Peak, we see integration into the porous areas, some integration here on the outside. This is the annulus out there. We also quantify everything histomorphometrically. So we look at what's in the walls, what's in the aperture for both type of implants. And we look at how much bone is in the aperture. We've got titanium on the left. It progresses with time. Peak on the right, it progresses with time. How much bone is in the walls? A little bit with Peak, a little bit with titanium. Just like the cancellous bone from all my studies from, the year 2000, is the bone to go into cancellous is quite difficult. This is how much implant there is. In the aperture, obviously there's no implant, but in the titanium, it was about 50% implant and 50% porous, where the Peak was about, 90% implant and 10% porous. So when we normalize bone in the available void, the aperture data does not change, but the bone in the available void demonstrates that both materials supported osseointegration into the macro topography that was presented. So really, can we start wrapping this up and hopefully have time for some questions? The models that we use are models. And so they're giving us insight in it, but always remember they are models. From a radiographic point of view, we again demonstrate the limitations of metal versus polymer. And again, from a manual palpation and a range of motion, both technologies supported fusion. From a histological perspective, both technologies supported fusion. So both of them worked. I think the biggest finding out of this is the radiographic limitations have not gone away just because the implant is porous. And it is a short-term follow-up. But, it's not surprising when I think about radiographic limitations. I mean, we've known this in the arthroplasty world and in the shoulder world and in the knee world in sports medicine for years. It's difficult with titanium to do some types of imaging, and just because it's porous doesn't mean you can see through it. And so you may not want to believe everything that you see. This is that case that was infected. And what we did in this was we put a profile line in image J just to get a grayscale analysis. You can see when the profile line hits the metal, it just peaks out at 255. But it's showing me some gray material in there. But and this is when we passed the profile line of that same device down through the aperture. And again, this looks like there's some gray value in there, or is it scatter? And it looks like there's something in the walls, but is it just scatter? And it actually is just scatter of the artifact from the CT scan of the metal. And this is what the histology looked like of that case, but this is what the micro CT looks like. So we did some micro CTs of some other specimens. This is from the study we did with Ken and Cambry. This is a micro CT of a cancellous TPMS system or implant in bone. And again, you would wonder, is that bone or is it artifact? And it's artifact. The bone is on primarily just gripping on the outside of it, not even coming into this structure here. So how bone interacts in what bone you put it in, or how an implant interacts in bone, is very dependent on what bone you put it in as well. So let's just play a little shell game for a second. Where's the P? Where's the bone? Okay, this is a commercially available implant that I just micro CT'd in my lab, and we filled it with, one has filled with autograft and the other one is empty. Very difficult to tell. Are all these little shadows in the wall, are they bone? Well, let's just look at that a little bit closer. This is time 0. This one has graft inside it. And yeah, maybe if you say, let's overlay these two because they're almost the exact same slice from a micro CT point of view, but very difficult to tell. So what we did, well, actually, just to finish off that thought, this is what happens if you do a profile line through peak in the current study. You can see this is a little bit of a grayscale value there, and then boom, that's our fusion. And if we pass the same profile line through the titanium, we peak out, that's ironic, but we max out at 255. We get something in the middle, but we're really not sure. This is actually this is the interface, like right there. What's happening at the interface, we cannot really tell. So we did another little study, and I have to acknowledge the team on the bottom, including Matthew Shumper, who printed these idealized titanium implants for us, kind of a TPMS system, an organic lattice, a truss, and again, just another lattice structure. And we printed them in titanium. But then when we got the models, we printed them in PLA because we have a PLA printer. We don't have a bond printer yet. And we printed them. And what we did was we took those implants and put them into the sheep spine, and we CT scanned them with 0.6 millimeter slices. So even potentially a little bit better than clinical CT scans. And you can see black is an air ball because it's actually air. And then we filled them up with graft and did the same exact spines. And if we go a little bit closer to that, this is what empty titanium looks like. This is one of the implants. They all look the same because you can't tell. And this is it filled with graft. I really can't tell what implant it is. Is it porous? Is it not porous? I can tell that there's something in there, but I really can't tell the quality. So it's hard to assess porosity. It's also hard to, this is time 0. So with no healing. And we did the exact same spines, and we put an empty titanium cage, 3D printed, and an empty peak cage. And you can see the macro topography, or sorry, not peak, PLA. We can see the macro topography of the plastic cage and nothing in the middle. But this is the empty cage under the exact same conditions with micro CT, 38 microns. And if we fill it with graft, well, there's nothing in the walls to begin with, but here at least we can see the trabecular architecture of the graft material, and there's nothing in the walls because there's nothing in the walls. So really, what should you take home from this discussion? I think all data is important for at every stage of it, be it at the beginning, the middle, the end, and now the human clinical correlates, and really material versus geometry. I think it's important to realize that the macro features can often achieve stability independent of the material. We've shown that in this study with Greg. We showed it in the study with interbody fusion as well. Where you put the bone or implant has a big factor on what the bony response is. So don't assume that just because it grows in cortical bone, it's going to grow in cancellous bone or growing into a spine. Now, in 2024, as you've seen with Mark's presentation, we can additive manufacturing can be achieved with PEEK. It can be achieved with titanium. Both of these technologies are obviously improving at a rapid pace. But I think, again, the imaging side of PEEK still, for me, is an important component. The ability to correctly and confidently assess the status of the fusion. And so don't think just because it's porous, it must be bone. And again, this is just to reiterate that fact: empty, empty, filled with grafts. Again, seeing the architecture. If it's important, we can tell clearly that is not integrated. And here are we not sure? So with that, what you see is what you get. Well, with PEEK, what you see is what you get, because radiographically, you can see through it. Difficult with other materials like metals, unless you look at the histology, but that is not done clinically. And that's what you get, and that's infected, but that's what we saw. So with that, I'd like to thank my team. There's Matt, Tien, Dan, and then there's Rebecca and Natalie. And this is my little puppy, Roxy, who graduated puppy school on Tuesday night. So with that, Robin, if there's any time for questions, I would love to see if we can answer.
Yes. Bill, good job. And we do have questions, so hang tight. First of all, again, just a terrific presentation. I'm just going to fire a bunch of stuff at you, and this will be a little bit like the lightning round here. And so I want to reiterate a couple key points. First of all, in your study, there was no statistical difference between the PEEK and the titanium, and at least in terms of outcomes. And it reminded me of one of the key points you and both Mark made, which was basically structure versus chemistry driving fusion. So if you have two implants that have the same structure, even though they're both additive manufactured, wouldn't you expect to have no statistical difference in the fusion that comes out of that? And it would appear the one thing that stands out above all else in that study is your ability to visualize what's actually going on. Is that right?
I think, Robin, in typical fashion, what I took 30 minutes to say, you said in a minute. So
wait, Bill, there's more. Okay.
Yeah, but I think ultimately, geometry, I think geometry is a very, very, very important component. And, I think, Steve Kurtz's recent paper talking about the porosity and the pore size. I mean, Dennis Bobbin and Charlie Yang taught us that in arthroplasty 30 years ago. If the pores are too small, the bone doesn't want to go in there. If the pores are way too big, it doesn't want to work. But, the porosity and the macrotopography almost makes the material irrelevant for osseointegration. It's not that it's irrelevant for mechanical properties. So you can't just take one component and just say, well, we could make it out of, marshmallow. That's not true.
Everyone should get in your brain, honestly. You just, make all of us make so much better choices. So if geometry is driving biomechanics, I'm assuming the whole underlying premise here is that biomechanics drives osseointegration, right?
Yeah, guess what? That's a fantastic point, because once you achieve some level of biomechanical stability at the interface, be it in the aperture or in the porous walls, the biomechanics of the whole environment changes. Because don't forget, we're not just talking about how strong a PEEK cage is or how strong a titanium cage is. We're talking about a single level motion segment that is basically moving around.
Right.
and you want to stabilize that. And as soon as you start to fuse, especially in the aperture, the stresses go off the implant and down the aperture. So it's a completely, so the biomechanics of the of the motion segment is not a static consideration. And the cage ultimately becomes a spacer to hold the bones apart. But I think the cages that people now are designing have elegant features that that will hopefully provide better ways for the body to integrate into to ultimately facilitate the clinical outcome.
So we're all the basis of this whole presentation, and I love this presentation. You and Mark are just awesome, is that the manufacturing method is going to affect the ability of the bone to osseointegrate or the implant to osseointegrate, right? That's
I
the
mean, I
whole
think the
that's
the manufacturing method does make a difference, but like the opportunity to make complex shapes with
yeah,
titanium is there. The opportunity
yeah,
to make complex shapes with PEEK is also there, right?
it's
So
coming.
they both,
Yeah,
well, I think it's there. I mean, I think it's
yeah.
there. The papers with the FFF and the FFD techniques with PEEK and the understanding that like Bond 3D has brought to this, and other device manufacturers and other companies that are working in the 3D space with polymers. It's fantastic.
Two more questions. Number one, is there a ideal type of bone? You keep talking about cortical and cancellous bone have different reactions. Does this additive manufacturing peak work better in one versus the other?
Um, I think that my point about the bones being different is that cortical bone is under different loads than cancellous bone. The architecture of the distal femur is different than the architecture of the lumbar spine in terms of the cancellous architecture. And that's
Okay.
where I would say it always confuses me, is that people say it's modeled after trabecular bone or cancellous bone. I go, which one? What bone? What patient? What age? They're all different. And you know what I find is there's almost like a trilinear curve. Everything in this little area works. There the, you know, the silver bullet? Yeah, maybe, but I doubt it. And is there ones that don't work? Yeah, there's ones that don't work, because the ones that are pores are too small. They really
Yeah.
don't work. But again, we know that data from our cobalt chrome and titanium osseointegration studies that, you know, Pilar and Bobbin and all the guys in when uncemented arthroplasty was started in like the early 80s, and even the titanium meshes that Zimmer put out, all of that stuff. So, you know, history is a great teacher, and history is the literature.
So let's transition to the future now. Look, after listening to your presentation and listening to Mark, if I was a surgeon, I would only go with additive manufactured peak. I really would. What do you now? That's just me because I jump on the latest thing, but what do you think is the future of spinal implant geometries and material?
I think the future of spinal implants and geometry materials is there's room for both technologies to coexist. When I talk to my clinical friends, they are concerned about the mechanics of the implants in terms of the properties of the implants, and titanium obviously is potentially stronger and stiffer. But I think that the radiographic limitations also throw another little spanner in the works. I mean, I
It
think both
does.
technologies will coexist. To say that one technology is superior for every application is probably simplifying the system too much. I mean, additive manufactured acetabular cups in titanium, unbelievable, right? You know, you look at
Yeah,
that stuff. I mean, our friends in the motherland in Italy, they've been doing that for years, you know.
that's
So I'm half Italian.
Italy's
My
the
mom's from
motherland.
Calabria.
Well, okay,
Reggio Calabria. Reggio Calabria. So,
there you
but
go.
you know what?
Okay, we have an Italian questioning us here. Seriously. So we have a question. Roughness porosity is really important, but what about chemical bonds? There are limitations of peak. What about angiogenesis properties that can favor osteogenesis?
I agree, Francesco, that that surface roughness is an important parameter, but surface roughness over macro topography, I'll take macro topography any day of the week. Would I rather be on the bone or in the bone? Right? I would rather be in the bone than on the. I would rather be in than on any day of the week biomechanically. and in terms of vascularity or angiogenesis, is that, if you get new blood vessel formation there, then you will get new bone. If you don't get blood vessels, you're not going to get bone, right? You need a blood supply ultimately for a long, stable, long-term clinical interface. So, I think looking at it at the cell-based stuff, we can see that some materials perform better cell-based. But as soon as you get to the macro world, i.e. putting an implant into the bone or putting a cage in between the end plates, there's a lot of other factors that happen in vivo that are not replicated in vitro in cell culture.
Amen. Well, that's the benefit of you having your models. You have a model, it's one model, test everything on the same model. Well, look, we are only 10 minutes past time. And I just want to say, having gone to, hundreds of meetings, listened to thousands of presentations, I love this masterclass format. You can really dive into a subject and really get to know it well. This one masterclass epitomizes, in my mind, why we do masterclasses. So Bill and Mark, you guys are the best. Really appreciate you guys so much. And look, we're gonna put up a slide here in a second. There it is. It's got a QR code. You can use that QR code to get put in additional questions, information, whatever you want. And I encourage the audience to really dive into this. And I know when we put this on YouTube and we're going to be putting it up, you guys all get a little email about that. We had one of our other master classes. We've had now over 10,000 views on YouTube. I hope this one also gets that kind of view, because the information here is fantastic. Bill, thank you again.
Robin, I just want to thank you again. You're the master moderator, the compare without compare. So I appreciate it, and I'd like to thank everyone for taking some time out of their evening. And it's what people often ask me, Bill, what do you think the future is? Like you just did. I'm actually living in the future because it's actually Thursday here.
Yes, you are.
And so I know what's happening.
Oh my gosh.
I know. I'm in the future already. Right.
All right.
So
okay.
I'll leave you with that silly joke.
Sounds wonderful. Bill, you're the best. And audience, thank you so much. This is the end of our masterclass. Again, take a picture of those QR codes, and watch for the recording on YouTube. Have a good night, everybody, and safe travels, Bill.
Thanks, buddy. See ya.